Well, hi there. My name is Kurt Moody, and I'm a professor of biology and environmental studies at Columbia College in South Carolina. And this is the first installment of a series of little video lectures that I'm making for my course this semester in environmental science, known as PS 148. I'm going to be doing a whole series of these, and you're going to be expected to watch them all and to follow them up with some homework questions. So get used to this type of format. I have some capabilities here. I can draw your attention to things by writing on the slide. And here we have the title of the material I'm talking about in this little video. It's Introductions, Introduction to the Course. There are some readings associated with this presentation. I'd like you to read the course syllabus, and I'd like you to read from a text called ITES, that's Introduction to Environmental Science. Chapter 1 from that text, the text is available in the course shell. This is how I'm going to get started. This is how this is going to look. Let's continue so that I can get this done. My goal is to have each of these little videos take about half an hour. The nice thing about video is that if you miss part of it or you have to leave, you come back, you can watch it over and over and over again. So let's not belabor this introduction because we're going to see each other pretty soon in class. And let's get going talking about what the class is going to be like. Okay, a little bit more detail here. This is me, and this is me, and this is me. I am the instructor for the course, Kurt Moody, and there are 4 texts which are available to you. The good news about these texts is that they are all free and available online. You can download the PDFs, or they each actually have websites that are available too, and you can kind of read them online. The reason there are 4 is because environmental science is a very interdisciplinary science. It's kind of loosey-goosey, hard to define. So I'm grabbing little bits and pieces of things from many different sources, and this makes it easier for me. I have some abbreviations here. ITES is Introduction to Environmental Science. APES is AP Environmental Science. ESCI is Earth Science, and CBIO is Concepts of Biology. When I give the readings at the beginning of each one of these little presentations, I'll be using those abbreviations to let you know. And again, these texts are all available in the course shell. The format of this course is a little bit odd. It's hybrid, flipped. I'm going to talk a little bit more about that as I go along here. That means basically that we're going to be meeting in class, but that's going to be for the lab meetings. All of the lectures are going to be these recorded, and you watching them on your own and doing the work on your own, which is a little bit odd, a little bit different for college students. And it may take some getting used to. So let's make sure that we understand it clearly and that we're staying in touch with what's required to be successful in this type of course. As I mentioned, these texts above are going to involve some readings. These are not necessarily the kind of readings that are like, read this chapter, I'll lecture on this chapter, and then we'll have a quiz on this chapter. It doesn't really work like that. I'm going to just be giving you parts of these texts that could be helpful in terms of you understanding the material. I would start with the lectures and then fill in the blanks with the readings. That's my advice to you. So that's the lectures are going to be built with PowerPoint. That's what I'm doing right here now. Narrated, highlighted, writing all over everything. I'm going to also give you some additional video links. This is all going to be available in these little boxes in the course shell. I'm trying to organize it as best I can. I will demonstrate some of the organization when we get into class with each other. And then there are also going to be homeworks in this organization in the course shell. They will be mounted as Canvas quizzes. Let's see. We're going to be meeting 2 times a week, Tuesdays and Thursdays. That's in the evening with you guys. There will be 4 exams. I don't want to get too deep here. There is a course syllabus. The course syllabus is one of your readings for this particular lesson. Okay, so there could be some, for instance, homework questions that relate to the course syllabus. This will take some getting used to, so let's just keep moving. Okay, so this is a little bit more about me. This is titled Who is Moody? And these pictures here should indicate to you that my background is in marine biology. Actually, technically, I am an oceanographer. That's important distinction because oceanography is an interdisciplinary science, not just biology. It's chemistry, it's physics, it's geology and biology. And environmental science is also an interdisciplinary science, so that fits in here. I grew up in Maine. If you head north along the coast and get to Canada, you've gone a little bit too far. I have a lot of pictures, a lot of stories to tell. Students seem to like that. I've been here at Columbia College since 2003, so 19 years. I like to get outside, do some field science, what I call field biology, and I like to engage in social and environmental advocacy, which is also very connected to environmental science. These pictures here show me doing things out in the field, plus a bonus picture of me in my lab with a whole bunch of students. And this could be you. And of course, I also have a family. Dr. Tamara Burke is my wife. She also works here at Columbia College. And this is my son, Roscoe. And that's enough about me. All right, I mentioned before in a previous slide that this course was described as hybrid flipped. So here's a little bit more detail about that. It's hybrid because it is both online and in person. The major components of the course, things like readings and lectures and videos and homeworks, those are all accessed online. The labs will be in person. Those will be our Tuesday and Thursday meetings. So hybrid because both of those things are part of the course. Flipped because of the fact that what we normally associate as the major part of the course, the primary meetings, is the part that's accessed online. So online, the primary part, the readings, the lectures, and the homeworks, and then the part that's in person is the lab part. And in science, that's fairly common because of the fact that the lab part is the part where we benefit most from being together as a community and working together. So hybrid, whole bunch of different approaches to education, and flipped because we are putting what's generally considered to be the important stuff online. I've got a little note here. I don't usually use this much text, but I really want to make sure that a lot of this is very clear. So I'll grab a highlighter here. This format will require you to engage in the class material outside of the class meetings. You will not be able to understand the material simply by watching the lectures and attending lab. A traditional 4-credit lab science course usually meets for 5 to 6 hours a week. All of our lab science courses do that. This requires an extra 5 hours of outside of class work. And so over the course of a 14-week semester, this adds up to 150 hours of student time. All of our lab science courses require that. I'm required to account for that time. The federal government requires that. So I have to prepare coursework responsibilities well beyond the scope of you watching these videos. Your self-motivation and conscientious engagement will be important for your success. We will talk more in person about how to approach this material and how to not get left behind, because it does happen. It's a weird course. Okay, so to illustrate this weird hybrid flipped format, I have a picture of a classroom here. Normally, this is what a college class looks like during most of your time engaged with it. We will do a little bit of time like this, but it won't look like this. Most of your time in this class will look like this. These people are looking at a screen with their earbuds in, their headphones. They are focused. They got some coffee or some books or something. They've got it. They're comfortable, but they are not engaging with anything else. They are focused on the course material, and they're taking notes, and they are making observations. So this is what you should be looking like when you are listening to these videos. You should not be driving your car with it in the background or cooking dinner or watching some other show at the same time. This is what students look like when they're engaging with online material. And this is what students look like when they are in my lab working together in an engaged um, activity that we're doing. We will be meeting in my lab, which is 111 Science Center on campus, Tuesdays and Thursdays from 7 to 8:15. It's only 75 minutes, but we're doing it twice a week. So it still all adds up to account for the time that I'm supposed to keep you busy. Okay, so I know that a lot of students are concerned about grades and what grades might look like in this course. This is a little bit of information about how I approach the grades and how they've looked in the past. This is a little distribution of how I determine the grades. This is what's called a histogram, which shows the distribution of grades in terms of how frequent they are. I do this out of 500 points, but these graphs don't show 500 points. They just show which grades were the most common. And the last time I taught this course, the two most common grades were an A and a C+. The average in the course was a B. We give these weird grades at Columbia College where there's B pluses and C pluses. But if you collapse those into just A, B, C, D, then it has kind of a nice normal distribution, a little bit down skewed. You might look at this and go, whoo, thank goodness he doesn't give any Fs. The reason there's no Fs here is because if somebody's failing my course, I go to them at midterm and I say, you need to get out because it will not make any sense for you to fail this course and then have to take it again. So I don't like it when, I don't like giving Fs. I don't like giving Ds either. But you know that the last couple of years with all of this pandemic stuff has been hard on all of us. So anyway, this is what the grades look like, and I'm happy to talk more about them as we go along. Okay, so in addition to grades, the other thing that students ask about quite a bit, maybe one of those FAQs, is attendance for the class. And this is kind of my attendance policy. You're expected to attend class. There's no such thing as an excused absence. I don't want to be in the position of trying to figure out whether your fiance's court date is more important than somebody's uncle's funeral. Those really aren't comparable. So we just say there aren't any excused absences, but I don't take off a lot for a whole bunch of absences until you get kind of serious about it. So we're talking about 1% per half of an absence, and there's a little formula here. If you're late, that's a tardy 2 times, then that's an absence, and tardy requires being 30 minutes late. This sounds very formulaic. I'm not actually that great at you know, following up on this, but if you're having an absence problem or a tardiness problem, it is going to affect your grade, and I might send you an email, say, hey, why can't you get to class on time, and please, you know, make sure that we're there. So it's not going to affect your grade. Anyway, this is just so you know what the policy is, and I'll apply this to the best of my ability. Okay, so here is some advice as we're wrapping up talking about how the class will work, and some nice happy people in my lab. And you could be like these happy people if you follow this advice. It says here, read lightly. That means that you can't just ignore the texts that I'm giving you. You should take a look at them. You should look at the pictures. You should scan the headings. You should read some of the parts that you're confused about, but don't depend on them in order to build the foundation for your understanding. That should be about the videos, and that's why it says watch carefully. Watch carefully, read lightly. So we can see that there's a balance between these two things. When I write exam questions, it's not going to be based on the reading. It's going to be based on what I say in these presentations. For the labs, you need to show up. You need to stay awake. It would be great if you could ask questions and take responsibility, because that's what we expect students to do when they're engaged in their own education. So if you can do these things, then, and I think a lot of these students in this particular class were actually education majors, so they know a little bit about learning and what it takes to be a good student. So here we are, Moody's advice. Okay, this is one last piece of advice. It says here, don't wait. Don't play chicken with me. Engage in the material right away. your first exam grade is a very good predictor of your final grade. This is a graph with an X and a Y axis. And if you remember some math from somewhere, the formula for a line is y equals mx plus b. There is no intercept here because it goes to the origin. So this is the formula for this line. Y equals 1 times x, basically, which means that that line has a slope of 1, and it's a fairly good predictor. X is the first exam grade and Y is the final grade, so the first exam grade is a fairly good predictor of the final grade. So don't say, oh, I'm not going to try until I see whether I'm struggling or not. Jump right into it. Okay, stay awake, be responsible. Got it? Don't wait. Okay, so that is some information about the course. I'm at about 15 minutes, so I've still got some time to kind of start the process of talking about what is environmental science, not just this course, but environmental science in general. So that's what I'm starting here. What is environmental science? Shouldn't be too surprising that it is a science which is focused on the environment, and I've underlined some words here that I think are pretty important. Environmental science is integrated, quantitative, which means it involves numbers and data and math, and interdisciplinary. I used that word before. It's not biology or geology or chemistry or physics. It's all of them coming together to focus on the environment. It is an applied science because we use it to address human-induced problems, not just questions we have about how the environment works, but how we're screwing it up and how we might be able to fix it. Or maybe it's not screwed up. Maybe we just want to control it or manage it. But it's about human influences. There's human systems and environmental systems. In fact, the next thing I have here is that it is a systems-based approach. So this is just kind of a list with some important things in it. And then down below, I grabbed a definition out of one of your texts. I don't know which one it was. But I highlighted some of the things in this definition which re-emphasize what I'm talking about here. So it says here, study of the environment, okay, and it is the solution of environmental problems right there, and that it is integrated, so we have that, and that it is quantitative, so we have that, and interdisciplinary, so we have that, and it is focused on environmental systems. Sorry, I just scribbled everywhere, but I want you to see that this definition and this list basically contain the same components. All right, so interdisciplinary is very important. Systems-based, which we'll talk more about, very important, and the fact that we're addressing human-induced problems. Okay, so this is a slide that I think is just supposed to confuse you because it's really complicated with arrows and dots and lots of things interacting. And this is the concept of the system, which often is confusing to students. But this complexity in this case is really trying to make it simpler. I want you to understand that a system is what we call operationally defined. That means that we create it with a particular goal in mind. It is a whole bunch of things that are connected to each other and interacting, kind of interdisciplinary, integrated, as we were just saying. But we're doing it in order to make a prediction that might be useful to us. It might allow us to draw conclusions and solve some problems. This seems to be about energy or information, so we might be interested in if we change the price of gas, what does that do to how often people go shopping? If we change access to the internet, how does that influence whether or not people are traveling in airplanes? These things are actually connected, and they have an influence on the environment. So we would be looking at a system like this, trying to figure out what are the inputs, what are the outputs, what is cycling within this system, and what type of feedback is there that keeps it stable or makes it cycle out of control? Stability, predictability, disturbances, okay? And then I've underlined two things here that are really important. The things that we're going to be measuring in systems like this in environmental science are generally matter, which is going to involve chemistry, or energy, which is going to involve physics. Boom, we're bringing two sciences together right away. So systems are complicated. They're operationally defined. We don't have to understand all systems at once. We have to understand a system that we're interested in using to make a particular prediction. And it's going to be about matter, which generally cycles within a system, and energy, which generally flows through a system. I'll say that again when we talk about energy and matter, which are coming right up. Matter cycles within a system, energy flows through a system. Okay, got that? Good. Okay, so environmental science is interdisciplinary, and it is integrated and applied, and it involves systems. This is a system that was developed by NASA way back in 1988. And even then it was really complicated, and it's just a nice example. I grabbed this from one of your texts. It's a nice example of different things that we might talk about in this class. Not all of them at once, maybe one at a time, to see how they engage with this system. For instance, we have the atmosphere. We will be talking about that. We have the sun, where a lot of our energy comes from. We have soil, which is clearly important in the environment. We have the sediments at the bottom of the ocean. We have climate change. We have a big box here that represents human activities because it's Earth systems interacting with human systems. Anyway, don't need to understand this right now. Just recognize that for quite some time, science has been creating this system, this environmental system, to see what components we need to understand so that we can make predictions about how the whole system is integrated, so that it's useful for maybe solving some of our problems. Okay, so a little bit of summary here. Environmental science is about how Earth systems and human systems interact with each other, all right? All the things that might control how the environment functions that we might have to understand independently and then connect together in a system concept, and then all the things that have an influence on human behavior, economics, upbringing, and culture, and things like that, and how those influence human systems, and how those two different types of systems interact. So I drew this picture here for you, thinking about the system of the Earth and the system of the humans, with all these lines showing them interacting in two different ways. And personally, I like things in threes, so I made 3 lists of 3 to kind of summarize how environmental science is different from maybe some of the other sciences that we focus on. There are 3 primary goals in environmental science: to understand this system interaction, to predict it, and to fix it if it's not working quite right. And we're doing a lot of that these days. There are 3 reasons for wanting to do it: because we need natural resources and we need to keep them flowing, because we need the ecosystems around us to continue to purify our air and our water. Those are called ecosystem services. And because we don't want to use everything up too fast, we want the environment to be able to create resources for us on a regular basis, which means we need to use them sustainably. So natural resources, ecosystem services, and sustainability, all 3 important reasons for wanting to understand this interaction between Earth systems and human systems. And then 3 differences between environmental science and other types of sciences. It's generally more applied. It's generally more reactive. In other words, oh, here's a problem, we need to do something about it. That's reactive, not proactive. And it is very often more personal and more political than other sciences. We have a lot of arguments about environmental science and what should be considered important and how we should apply policies to try to control human behaviors that might be interacting with the environment in ways that we're not too happy about. Personal, political, touchy. Okay, so 3 goals, 3 reasons, 3 differences. These aren't facts. These are just my take on how environmental science is maybe different from what's happening in other science courses. Okay, so complicated and system-based and lots of humans and environmental systems interacting with each other. But another thing that's really important to know about it is that environmental science is recent. It is not an old science. It is not one that we've been fixing human problems with the environment for a very long time. In fact, it can be traced back to events that happened in the late 60s and early 70s in the 20th century. This is one of those events, and it's a very important one, and it really changed everything, really. It changed the way that humans interact with the world because it changed our view of the world. This is a photograph. It's called Earthrise, and it was taken by an astronaut named William Anders, who was orbiting the moon in 1968. And it was taken as the orbiter came around the moon in the Apollo 8 mission, and it made it. It's kind of the way that we have a sunrise coming up on the horizon of the Earth when we look across the ocean. This is the Earth rising on the horizon of the moon, and it's very pretty. But when this photograph was released for people to see all around the world, it was just at about the same time that lots of environmental issues were coming up. Pollution and problems like, for instance, Rachel Carson had recently written Silent Spring. Lots of things that people were concerned about, and people looked at this photo and said, oh my goodness, it's really small and there's no place else to go. And it made us see for the first time, I don't know if you can imagine a world in which a globe that you're using is basically an interpretation that's not based on any type of photography. This is really the first photograph of the Earth from space. Okay, so it changed the human concept about the Earth and the environment around the Earth, and things happened really quickly after that. Here are some things that happened. 1968 was Earthrise. 1970 was the first Earth Day. And also in 1970, the Natural Resources Defense Council was developed. In 1970, the National Oceanographic and Atmospheric Administration, NOAA, was created. The Environmental Protection Agency was created. The Clean Water Act was drafted in 1972. The Coastal Zone Management Act, the Marine and Mammal Protection Act. Many, many things happened very quickly because suddenly there was a lot of attention on concerns that people were having too much of a toxic influence on the Earth around them. So this is just to indicate that with this time of Earthrise, this is when things started to happen, which made the practice of environmental science very applied, very political, very personal, just like the things I was just talking about in that last slide. Okay, so environmental science is complicated, it's integrated, it's systematic, it is applied and interdisciplinary, and so complex that in fact we have other terms that get confused with it. This is a word cloud, and lots of the things that come up on the internet can be shown, and the size of these words indicates how often they show up in association with environmental science. And there are 4 terminologies here that I want you to be able to distinguish, okay? The first of it is environmental science, and this is what we're studying here. This is in a science class, so we're going to be using scientific tools and scientific logic. Here at Columbia College, we also have an environmental studies program. You can minor in environmental studies. That is more interdisciplinary, more focused on human creations like literature and art and laws and things like that. So that's more focused on the human systems side of things. There's a word that we use quite a bit. It is environmentalism. That is not the same thing as being focused in the science of the environment. That is about the politics of the environment and the personal nature of the environment. When a person is prioritizing sustainability and environmental health, they are being an environmentalist. They are raising the importance of the environment relative to all the other things that humans might think are important or not so important. Okay, so environmentalism is more of a political or a values-based area of interest. And then finally, the last one here is ecology, which actually gets used interchangeably with environmental science quite a bit, but environmental science is more interdisciplinary and ecology is more about biology. I actually teach an ecology class here at Columbia College, and it is a biology class. You have to be a biology major actually to take it. So it's focused on living systems and not just Earth systems. Okay, pardon me. 30 minutes, last slide, bam, drops mic. I will see you guys in class. You are now prepared to do the homework for this, and hopefully I've got it organized in the course shell so that it's clear what you have to click on in order to get that done. See you on Tuesday. Bye.